forth. So now, good morning, and this is Jim O'Brien. Today we're going to talk about the part 2 of the sediment supply for mud flows. Now, last week was part 1. I discussed the physical process of mud flows. So today we're going to talk about balancing the sediment supply with what you're predicting in the flow 2D model so that we can assess the appropriate type of flow that you're going to get, whether it's a mud flow or a mud flood, as we discussed last week in the physical processes. So if you wanted to review the physical processes webinar, you can download that for free. It was recorded and posted on the website. Okay, let me move my Okay, so the objective of the Flow 2D, a Flow 2D model simulation with Mudflow is to match your estimated sediment supply with the storm water volume that you have as your design event, and then balance these two with the output from the Flow 2D model. So that's what we're going to get to as a final product in this webinar today. So let's start by, hold on a second here, I got to use my mouse to do this. Okay, so let's talk about the physical factors contributing to mud flow to begin with. Depending on your basin and where you are around the world, perhaps, you're going to have different watershed conditions that are going to contribute to the potential development of a mud flow. So I'm going to focus on mostly mud flow that's generated by hydrologic conditions, as opposed to like a volcano or a landslide hill slope type of event. But we'll discuss those a little bit too. So what I'm going to indicate to you is I'll show you some drainage and channel development that you should see in the field that may contribute to mud flows. And what we're going to try to do is to estimate the sediment availability and what are the major contributing factors to the sediment supply. Sometimes exposed slopes will be a major contributor due to either fires or logging or some other reduction in vegetation. Oftentimes debris, which typically is either organic debris or boulders, can include some trash in some areas where you might have a trash dump in a side canyon or near an alluvial fan. That can contribute to the frontal wave too. And we'll talk a little bit about roughness and constriction. So these are the things that you should be aware of in the watershed that may contribute to the mud flow. So let's start with drainage and channel development. And in this case, what I encourage you to do is to walk up the watershed from the fan apex or canyon mouth up to where you're looking into the upper watershed where the water is being contributed from. Now, what the things that you want to observe when you're in the walking up the watershed is, how much sediment is available in the channel. Has the channel been restored to a previous state, or is it still scoured to bedrock? Typically, if you go up into a channel after a mud flow event, you'll see a lot of exposure of the bedrock on the bed of the channel. And you'll see some undercut banks and maybe some hill slope failures. Document all of these because this will help you in estimating your sediment load. Now, if you've had 10 years or say 25 years since the last major mud flow event, then you would expect to see a lot of sediment stored in the channel, that the water course is recharged with sediment, and perhaps you're looking at uh, a situation where there's been a recent fire, but not a rainfall event on top of the burned area that may contribute to sediment loading. So in order to check for a mudflow potential, um, look at the nature of the historic events on the alluvial fan. This would include any channel or fan deposits, whether you have natural bouldery levees or low bay deposits. Um, how much loose debris and boulders are in the channel? Again, is it recharged? Take a look at the fan slope. Typically, it's steeper for mud flows. It's more mild for non-cohesive mud floods, like in desert alluvial fan situations. The fan break and there may be a fan break and slope where the mud flow deposits of the frontal wave typically occur, and so this downstream of that point, there may be a flattening in the slope. Look for fan hummocky deposits, and I would definitely encourage you to take some sediment samples back to the laboratory or pay to have them done, and at least get a sand silt split so that you understand how much silts and clays may be in the deposits. If there are a minimum of silts and clays in the deposits, then it may behoove you to also get a hydrometer analysis and see how much of the fine sediment is actually clay material, which would define whether or not you're going to have a mud flow or a mud flood, as we discussed last week. So with mud flow fans, you might look at a very steep slope, as you note here. It's fairly steep. There may be frontal wave berms, an uneven surface. As you walk around on the fan, you might see exposed boulders and unsorted deposits. But what's very clear here is the nature of the hummocky deposits down on this slope. You can see them here throughout the fan development. You can see them higher up, but right now this channel has been isolated to one side of the alluvial fan for recent events. However, the next event, being a mud flow event, may come down and just overwhelm this channel and proceed either straight down the fan or more to the opposite side. So it depends on what side of the fan is still being developed. So when you're walking up and down the channel, look for the opportunity for the flood to contain itself by developing its own natural levees. Now, we saw an extreme event in a movie last week that it did that. Here, the natural levee development is formulated by boulders to the most extent. However, this particular event has been washed. In other words, after the mud flow came through, either on the recessional limb or during subsequent rainfall events, there's been less concentration by volume of sediment loading, and it's washed some of the surface material out and exposed the boulders. So the primary supply of sediment comes from 5 principal sources: landslides, or in a smaller scope, hill slope sloughing or failure, which are just small scale landslides essentially; channel bank failure; channel bed scour. And I highlighted these in red because typically for a hydrologic initiated event, these will be the primary sources of sediment. Then overland sediment yield, and other possible mud flow sources of sediment might be volcanism or dam failures. And again, the objective is going to balance your estimated sediment supply with the computed sediment loading. So the primary sources in this case may be bed scour. So the next event coming down here is going to peel off most of the sediment here and drop it down to bedrock. And you can see that here. Or you might have an undercutting of the bank in this case, and it may either initiate bank failure or hill slope sloughing down into the channel. Here we see the limit being a scour to bedrock. In some extreme cases, you may see severe hill slope failure or landslides to generate a mud flow. And then finally, a burn condition will greatly contribute to the overland sediment yield. So let's start with overland sediment yield and how you might estimate this. Typically, this is more of a back of the envelope type of calculation. The overland sediment sediment yield is considered as sheet flow erosion, and I computed or estimated with the revised universal soil loss equation or modified soil loss equation. These are the NRCS methodologies, and you can uh, read about those methodologies and so forth by just typing in Roosley or Muesli NRCS on a Google search. These are typically a yield rate in tons per acre per year or so, and you'll want to compare these maybe with a pre and post fire condition if that's what you're trying to do, is estimate the potential for mud flow after a burned condition. And they can be pronounced much different from the pre-fire condition. When you have an increased fine sediment loading due to either denuding the vegetation or because of a fire, the increased sediment concentration will obviously change the size fraction distribution, but it'll also, during the event, mud flow event, decrease the particle fall velocity and increase the buoyancy of the large clastic material. This results in the entrainment of much more of the coarse material and leads to the unsorted nature of the deposits. It also increases the fluid matrix viscosity and yield stress components, and that's why it's important to estimate the the fine sediment size fraction. So to simulate a mud flow, what we have to do is estimate the sediment supply volume, including the overland sediment yield. Know the inflow hydrograph or design event that you're going to estimate this, and then we're going to distribute a concentration by volume to the design hydrology flood event on a time discharge pair scenario in the inflow.data file for flow2D. The objective for mud flows is to get an average of concentration by volume of 30 to 35%, with the peak concentration somewhere around 50%, or if you remember our table last week, for mud flows, it's 45 to 55% concentration by volume for a mud flow event, and like 20 to 45% concentration by volume for the mud flood event. The peak water discharge and the peak sediment concentration by volume never coincide, and that's because the peak concentration is generally associated with the rising limb of the hydrograph or the frontal wave, and the peak water discharge, by the time it arrives, will dilute the concentrations. So you're going to have a much smaller sediment concentration during the water peak discharge. And what'll happen is the peak water discharge will catch up with the frontal wave and become one frontal wave peak discharge event. And then later on in the presentation, we're going to compare the sediment and the water volumes with the sediment supply to estimate this and see if we're in the 30 to 35% concentration by volume. So let's see how we would approach this. We might look at an overall area and see if there is some hill slope sloughing or landslide conditions in the upper watershed. Um, we may look at a watershed, if it didn't have any of these two, that the principal sediment supply is going to occur in the well-defined channelized portion of the upper of the watershed, the kind of the canyon portion of the watershed above the alluvial fan apex. And then the overland sediment yield in this case may be limited to an upper region or along the upper portions of the canyon reach of the watershed. So let's take a look at a movie here that I selected for you. And the objective of this movie is to show you the differences between the sediment supply and the water volume. Here you see an eroded portion of this watershed contributing sediment, and it's starting to contribute now. You can see the discoloration of the water event coming down from one portion of the watershed, and the mud boulders and debris being loaded from the other portion of the watershed. So here we see the development of a frontal wave, and yet the hydrology is still catching up with the frontal wave. So here we see the boulders both retarding some of the flow and also becoming part of the frontal wave in the development of the mud flow. So in a very short reach of this, we've seen a mixed flow of mud flow and mud flood. Now it's basically a mud flood, somewhere in a concentration on the order of 30 to 35, 40%. I'm going to play this again so that you see it again. Here you see some of the mobilization from a hill slope for sloughing failure, maybe some scour and bank erosion occurring here. And you can see the discoloration occurs, but most of the hydrology is coming from another portion of the watershed. So these are the kind of things that you need to observe when you go up into the basin. Combined with what you may see on the alluvial fan will determine if you're going to have this kind of mud flow event, which this is kind of more of a debris flow event, but the concentrations in this frontal wave are probably on the order of 45, 50% concentration by volume. Now it's dropped back to maybe 40 to 35% concentration by volume, much more fluid event. Now I'm going to show you another one of these movies. Let me pause this there. And this is a continuation of the previous event, but just downstream in the lower canyon area. So you're seeing that this channel was somewhat charged with sediment, so it's continually contributing to this frontal wave. But the peak discharge is basically caught up more or less with the frontal wave, and the peak flood event and the rising limb of the hydrograph are essentially one and the same. So let me play it again for you. So you see there's quite a bit of debris here, some additional loading of water. Here comes the frontal wave. This larger, coarser material is essentially caught up or is in the frontal wave, and the peak has passed, and the frontal wave is basically the peak flow. It's a very short-lived event. So these kind of mixed flow events are important to understand because you may want to mitigate for the mud flow frontal wave, but yet still the overall event is going to be maybe in the realm of 30 concentration by volume, and it may reflect more of a mud flood event. So to finish our supply calculations, along with the overland sediment yield, which I briefly discussed before, I'm not expecting you to read this or understand it. It's more for my uh, to remind myself of what to talk about during the PowerPoint here. This is somebody else's estimate of what the potential sediment supply is. So they did this, just with notes, but in terms of the bed scour estimate, this is a well-defined channel. It's about 240 feet in length. You can estimate that in an aerial photograph or whatever. It's an average of about 5 foot in width. The material in the channel is well sorted with a matrix D50 on the order of about 2 inches. It's a mixture of sand up to boulders. So assuming a scour depth of about 3 foot, which is consistent up and down this channelized portion of the watershed, this would yield a volume of about 3,600 cubic feet from the bed scour, and amounts to, in acre feet, about 0.03 acre feet. Now, if you scour the bed down 3 feet here, then you're going to get sediment loading from bank failure. So in this case, it's assuming that the banks are relatively uniform. They're steep and narrow. You're going to wind up with an incised canyon here of about 15 feet or so. Assuming the current slope is 2 to 1, and it may result in a slightly steeper slope, each bank will lose approximately 180 square feet over the 240-foot length of channel. So you're taking a couple of trapezoids here, maybe a rectangle at the bottom for the bed scour, adding these 2 bank scours to it, which are trapezoids, and you can do the geometry. And this will yield a lot more sediment than the bed scour will. And then the overland sediment yield was computed for the upper watershed using Roosley, which is the revised universal soil loss equation. And in this case, the estimated Roosley, I think, is about 325. So it actually exceeds the bed failure and bed scour in this case. So the total available sediment supply in this case is, say, somewhere on the order of 5 acre feet. Now, if you have some doubts about this, you could say, well, I'm limited in my ability to make this assessment because I didn't go all the way up the channel or something. So you could multiply this by 1.5 or 1.25 or even 2 if you, depending on your level of uncertainty. In any case, if you came up with, say, 5 acre feet of sediment, then you can compare this with your design event, the 10-year, 25, and 100. In this case, 44 acre feet from water yield from the 10-year event up to the 100-year event being 9 acre feet of water. So if you combine the 2 events, then you can, or combine these 2, it'll give you a total sediment and water volume, and you can divide by the sediment volume to get the average concentration. Now, when you do this, you start with your water design hydrograph, time and discharge in the inflow.data file. And to this, we're going to add a sediment concentration by volume. Now, what I did was I loaded this up to 45, or roughly a Mudflow event, reflecting that movie a little bit on the rising limit of the hydrograph here, and then decrease the peak concentration somewhat when the peak water discharge arrived. So I distribute it this way, with the rising and falling limb parts of the hydrograph being at least 20% concentration by volume, which, if you remember the table last week, delineates the difference between a hyperconcentrated sediment flow event and my definition of a conventional bed and suspended load event, which this is a little high for that, but the concentration by volume of 25% to 35% is going to be basically behaving like water yet. So up to 20% by volume, you won't see any significant contribution to the viscous stresses from the sediment. So it's okay to model these as water. And so that's why I put the concentration by volume as 20%. Now you have also the option to add the sediment volume to this file. If you don't want to use the sediment concentration by volume, you can estimate what a yield might be, say, at the fan apex, and apply, or someplace up the valley or up the canyon where you want to have the sediment loading occur. So you could extend the flow 2D model up into the actual watershed or canyon area and add a given volume of sediment. It's the same file and it's the same format, except that this is greater than 1. So the model recognizes that it's going to be a sediment volume because you're applying a value that's greater than a concentration by volume of 1, where the maximum would be like 60% concentration by volume, or 0.6. So here's how you could load this at a given point in the watershed. Then when you run the model, you could run the model, say, for a simulation time of 1/10 of an hour or 100th of an hour, and it would compute the water volume in the hydrograph and the bulked sediment volume for you. And you could see this, decide whether or not you needed to add sediment supply or what the relationship was here. It also would print out the volume, the hydrograph with the bulk sediment volume computed in it, the total volume sediment computed in it, and base dot out if you wanted to review the actual hydrograph. But this is the computed bulked sediment yield. So the difference between these two, subtract the water from the bulked sediment or total volume, and you get the sediment volume from it. So if you divide, the difference is 14 acre feet, you divide the 14 acre feet by the total, and the average concentration in this case is around 38%, which would clearly indicate to you that you have an opportunity to have a mud flow or a mud flow frontal wave. And so going back now one, if you go back to this slide here, you want your average again to be somewhere on the order of 30 to 35% concentration by volume, with the peak on the order of 50%, that is 45 to 55% concentration by volume. And in this case, I had 35%. So it's well that it could be it's well understood that this could be a mud flow event that is more or less uniformly mud flow throughout most of the hydrograph. So in the end, you want to do several mud and flood and mud flow hazard scenarios. One is you could do a water flooding if you wanted to just show the client what the 2-year, 5-year, and so forth are for water flooding. Then you could assume that the water flood is going to be a conventional sediment transport event, and just bulk the concentration by 20% with the X concentration factor in the cont.data file. In other words, you don't have to apply this to the inflow.data file to do this low concentration event. It's going to behave like water. All you need is to bulk it so you can enter the X concentration by volume. It's just called XCONC in cont.data in the control.data file. And then it will bulk your water flows. And so the primary effect of this is not an impact on the fluid or the flow properties. It's just bulking the flow itself. It's not, there's no impact on the fluid properties, viscosity and yield stress, etc. It's just that the impact is only bulking the flow. So in a sense, if you're going to do mapping, it makes more sense to do the mapping with the low sediment concentrate, bulked flow sediment concentration, not the water flooding, which is literally impossible to have a clear water flood. And then map your mud flows with the concentration being variables, greater than 45%. Now, typically, I recommend that you're going to have a mud flow for a 10 or 25 year hydrologic event, but only a bulk flow for the 100-year event. And that's because in the 100-year event, there's typically way too much water for what your sediment supply will be in your basin. So if you took your sediment supply and bulked it by 2, and then compared it with a 100-year event, in most cases, you're still going to only be somewhere around 20% or less by volume, because there's just way too much sediment or water for in a 100-year design event for mud flow. So if you see a mud flow come down and it's viscous mud that occurs throughout the event itself, both on the rising and falling limbs, it will probably be on the order of the 10-year event. Once you're up into the 25-year event, you're going to see rising and falling limbs with a fall off in the concentration back down to, say 20% concentration by volume. So let's talk about how to map these different types of events briefly here. You can do a series of maps, and what I recommend is a flood inundation map and maybe some hydraulic intensity maps, that is the predicted maximum flow depths, which is nothing more than the flood inundation, and maximum velocity. And you could do these for existing conditions, and or possibly maybe you're designing a new feature or development for the alluvial fan or mall or something. And so you can put in these existing conditions and put the design event over your development. You can also generate hazard maps, which will show high, moderate, or low hazard. In Flow 2D, you can do flood hazard mapping with the Mapper program. The hazard maps are a little easier for the public to understand and to simulate, especially in public meetings. The hazard maps consist of 3 flood hazard zones, and these are a discrete combined function of the hydraulic intensity or severity of the event and the frequency of the event if you want to use the frequency in developing the maps. The hydraulic intensity is given by some function of the flow depth and velocity. And if you're using the frequency, you need 3 simulations, 10-year, 50, and 100-year return period events. So the 3 hydraulic or the 3 types of maps are shown here. One is the depth, maximum flow depth, and this becomes the area of inundation map. Maximum velocities, which would show you that the maximum velocities are generally along the most active course, water course of the alluvial fan or flood area, peneplain possibly, and the hazard maps, which show the high, medium, and low hazard potential. So a word or two about the hazard maps. These are easy to develop if you just go after you plot and mapper the maximum flow depths, then you can just go over to other map command and click on the hazard maps, and you'll be able to plot these maps up, and I'll show you what they look like here in a second. Um, uh, the hazard intensity, you do have a choice. You can do it by depth, or depth and v squared over 2g, or the one that we typically use is a combination of depth and velocity times the depth. So in USA, the typical hazard intensity is given typically only as depth. In other countries, it's given by depth or velocity squared over 2g. We're using in the hazard maps the depth and the velocity times depth, whichever is the worst case. So these intensities, what we're going to do is plot these as a function of intensity, and or if you use the 3 different frequency events, will be the frequency is plotted on this axis. So a high intensity map and a high intensity, high frequency event means that you're going to have a high hazard for a lot of the events, or a lot of the mapping, because this is a very frequent event, like the 2-year event. If it's an infrequent event, here it might have like the 500-year event, the probability of exceedance is low. So the actual plot might be a low hazard. So you'll see that in a minute. So we're using different hazard plots, which are a relationship of the flood depth and velocity. These are all hardwired into the mapper program. These particular hazard maps were promulgated by the United States Bureau of Reclamation, and they're pretty accurate. For example, I've gone out into collected data in river channels, and when you're at a depth of 3 to 4 feet, that is, the flow is getting up on your chest here, 3 to 4 feet on your chest. If you get into 3 feet per second and the flow is on your chest, you cannot stand up. It'll sweep you off your feet. So this becomes the high hazard zone, danger zone. So my own personal experience is that these are relatively accurate, and they're flood hazard for adults, for houses, for cars, etc. So we programmed these into the mapper for you. You can create your own definition of these maps for different colors of the plots, red, orange, and yellow, high, medium, and low hazard levels, to disseminate to the public. For high hazard, I generally define this as people are in danger inside and outside of structures. Buildings are capable of being destroyed. In a medium hazard, people are in danger outside of structures. Buildings may suffer damage or possible destruction depending on their types of construction or construction materials. And then in low hazard case, people can generally walk around in it. The danger to people is low. It's shallow flooding, but the shallow flooding gets inside the buildings, and they have damage due to, mud stains and interior flooding. Now, what you're going to get when you choose to do the the hazard maps in Mapper, is you will get a table, and you fill in these values. So for water flooding or for mud flows, you have the option to modify these numbers to your own judgment. There may be default values in there for you, but typically, say for 3 foot or higher, it's a high hazard, or a depth and velocity up to 1.5 square meters per second, or this would be, roughly 4.5 or so feet squared per second, something on that order. Or sorry, no, that's wrong. 10 squared feet per second, something like that. Um, you, you can make up these values as you need to. So, obviously it's lower if you have a mud flow or mud flood event or debris flow. If it's higher than a meter, you're going to destroy your house basically, and so forth. So you get the idea. So you can fill in these charts, and then when you choose to do it with frequencies, you've already done 3 simulations in 3 separate folders, say the 2-year, the 5-year, and the 50-year, or the 2-year, the 10-year, and the 100-year. And these results for mud flow or for water flow are in each one of these folders. And then the model will, or the mapper program will ask you which folders to select. And then it will interpolate the high, medium, and low hazard areas for you. And the end result will be a colored map similar to this, showing you the high hazard, the moderate hazard, and the low hazard areas of the alluvial fan. So I would combine these high hazard maps with possibly a water flood map or a water flood bulked with sediment map up to 20% concentration by volume, showing the inundation area as the water flooding came down and then stayed in the channel the rest of the way or into the stormwater system, which you could model with the mud flow too. But along the interface between the watershed and the urban area, these storm drains are just going to be clogged with sediment. And so it may be ineffective regardless of whether you're doing it for water flooding or not. But you could model the storm drain with the water flooding or the mud flow. And you can see here that the water flooding extends somewhat further down and into the urbanized alluvial fan than the mud flow. So you're mitigating for 2 types of events here, and your mitigation measures and your area of inundation um, for flood insurance, and your emergency access and your evacuation routes all have to take into account both types of flooding, because the watershed, as I tried to explain to you today, may not deliver a mud flood or mud flow event on the next occasion of storm rainfall runoff. And it's up to you to not only define what the next storm would be, or better yet, to design the evacuation to mitigate the flood hazard for both types of events. But I would define the flood hazard to the general public with these types of maps so that they could see that their home is in a high hazard area, and not look at this just in terms of a flood insurance rate map in which you have to know the base flood elevation and the water flood elevation in order to determine whether you're going to be inundated or not. I think these hazard maps are far more definitive. You can also panic the general population with these maps, but so you have to be a little bit discreet maybe in doing so. So um, last week, again, I did the physical processes of mud and debris flow. There are some other companion webinars for mud flows that I've done in the past, and I'll do again in the future. In later in the spring or summer, I'll do the Mudflow mitigation webinar again for you. And then we'll do a series on post-flood hydrology and mudflow generation and the impact of fire impact on runfall and mudflow generation variability with fire severity and so forth. So I encourage you to either review these past webinars or um, uh, keep your heads up for the next one that I do on hydrology and mudflow fire response. So let's see if there's any questions. I'm going to stop the recording.